Okay, thanks. All right, so hello everyone. I hope the first week of classes is going well. I don't know, you think the first one is always the toughest, and being on this side doesn't really change anything. So last effort, and then we have a break. So before we start, what I did Wednesday, first thing I did, I went back and I watched my own lecture, of course. First time they record me, I had to do that. So I had an epiphany. My accent is much worse than I thought. There's nothing I can do about that, I'm sorry. The other thing that I found out is that I missed a couple of pieces of information for you that I think are important. So I don't know how many are in the PhD program here. You raise your hands. No PhDs? Some PhDs. Well, definitely for you, this topic is going to be part of the qualifiers, I believe, right? Or most likely. So I'll be one of those writing some of the questions for that exam. There's a few more colleagues in the department that write the other questions. We basically usually share it, one question per professor or something like that. And so this class is intended to teach dynamics, of course, at a graduate level, but also to prepare you for that exam. So what I'm teaching here and the way I'm teaching this class is consistent to, I'm trying to be consistent to what others do, just for your own sake. Been teaching spacecraft attitude dynamics a few times, and I used to basically use different symbols, and some procedures and approaches were slightly different. The final results were, of course, the same, but I'm trying to stick to what we do in this department, and you should have no surprises at the qualifier exam, if you study, of course, and you understand the material. So there was a point that I wanted to make. The other comment is about your tests, and how many have really read the syllabus at this point? All of you, I hope. I really hope so. So you have two tests that you take home, 24 hours. Your graduate students, I trust you. I treat you as colleagues. You're not going to work with each other. You're not going to cheat. I'll find out if you do, believe me. So you have plenty of time to do that test, those tests. They don't take 24 hours, of course. But I don't like rushing graduate students who really have to think through the concepts to solve something. So I don't want to time you. So that's why I'm giving you a test that you can take home. You should expect, though, a little more than just problems to solve. We should expect conceptual questions. Maybe I'll ask you to demonstrate a simple formula with the tools that you should have. Not big demonstrations, of course, but you should expect some conceptual questions. So that's just to give you an idea. I have dates for those tests, but as we will approach those dates, we'll figure something out. If those dates don't work, I can give it to you over the weekend if you prefer. We'll see how things go. So as we get closer, I'll poll you, I'll send an email, I'll see where we stand, and we'll agree on which day, what time I'll give it to you. Then you have 24 hours to email it back to me, if that makes sense. The other comment is this midterm survey that you may have seen. It's 5% of your grade, so I'm sure you've seen it. So this is not part of the procedure that is followed at MAE or in the College of Engineering, I believe. You just have a final evaluation that you give of the class and the instructor. But I'm used to having a feedback in the middle of the semester. I really value that feedback. And so I decided to give you a survey and give you some points for that. So why not to do it, so that you have an incentive. And so I'll give you a PDF at some point. You print it out, fill out the form. It will be anonymous, of course. The idea is that you turn it in with the TA probably, maybe in a box, so she doesn't know who you are, I don't know who you are, and you can just express your concerns, if there are any. Believe me, there's nothing you can tell me, unless you're offensive, that can upset me. If there is something going on with the class that is not right, that becomes a concern for me, not something that upsets me. It's something that I want to know, so that's why I'll do that. And it will be, I think, right after the first test, so you have enough information to tell me how things are going, okay? So those are the two things that I wanted to tell you. I think they're important. If there are no questions, what we'll start to do today is... Yes?
Would there be software requirements for the code? Like any coding MATLAB?
No. It's just you, piece of paper, thinking. No MATLAB, no coding, nothing fancy. It's just applying what you see here. What you should expect is problems that are similar to what you see here, what you have in the book, nothing that goes outside of that. Because again, this is going to be consistent with what you see on your qualifiers as well, for those of you who will go through the qualifiers. Those who don't, well, that's dynamics. That's how you want to do dynamics anyways. Okay, so today we'll start kinematics. And it will be for a few weeks. If we don't understand kinematics right, if we don't know how to do kinematics right, every single step, there will be no point for you to keep coming to lectures for kinetics. No point whatsoever. If you remain behind on this, you're going to be in huge trouble. So this is really the basis of everything, is the geometry of motion. Now, the algebra is the geometry of motion. So what kinematics allows me to do, or basically what we do in kinematics, is representing motion, of course, using, and I should probably use half of the board. I think they're hating me from behind that glass. Representing motion using some chosen parameters. There is one more sentence that I want to add, and that is kinematics. So if you want, this is 1, 2, and 3. Does not focus on what?
The region of motion.
Exactly. On the causes of the motion. That would be kinetics. We just care about looking at what's going on around us and being able to represent it without understanding why it's going on. That will come after. Why? Well, because, and again, I'll keep writing this, and we're not going to do it for a long time. This equation, which we commented, is going to be valid in particular reference frames. It's a vectorial equation. Force is a vector. Acceleration is a vector. With kinematics, you're going to be able to express this. There is no point in even looking at this expression if you don't know how to write A, acceleration of a particle. And you can do it in many different ways. And of course, it depends on your point of view. OK, so before we start, with what we'll do today, we'll start taking derivatives. That's really what we do in kinematics. Let me add one more sentence here, and I'm going to break it in two parts so it makes it easier. In kinematics, we want to express two sets of things that come in this order: angular velocity and acceleration, and this means angular acceleration of reference frames. Only after you do this, you can compute or express velocity and acceleration of points in E3. That's all we do. And I'm going to go over the definitions that we gave last time a little more in detail. There's a few things that I left out. So if you think that I'm brainwashing you with a few concepts here, the first few weeks, or the first few lectures, yes, I am. And if you think it's boring, well, enjoy it until it lasts, because at some point we'll speed it up. But these are very important things. If you don't do this part right, the rest doesn't make any sense. So we'll go slow over these until we have a good grasp, and then we know how to use it. All these things are vectors, right? So the things that we've seen last time, first, E3. I'm not going to go over this. This is where we live. We wake up in the morning, surprise, you are in E3, like yesterday, and like when you were born. That's where we live, and that's where we operate. That's where we are looking at things moving. All these objects here are vectors. And vectors are reference frame independent. Does not matter where you are. This vector is what it is. Doesn't matter your point of view. Then, since in kinematics we're going to talk about rates of change of positions, as you can see here, these are velocities and accelerations. Those depend on your reference frame. So we have defined reference frames as, and I need to add something here. We call them sets of at least three non-collinear points whose mutual distances are constant. We also said something else last time, that reference frames are rigid bodies, and vice versa. Now, a rigid body can be massless for what we care. You could define a reference frame which is made of 3 points, made up of 3 points in E3 that don't have any mass, as long as they remain at mutual distances that are the same and they're non-collinear. That's a perfect reference frame, and you can call that a rigid body. Then it can be a rigid body, but it doesn't have to be. You can pick your reference frame when you wake up in the morning in E3 and you decide that you want to run some experiments. You pick your reference frame. It can be an object. It can be your table or not. It doesn't have to be a physical object. As long as it's made of 3 points, you fix yourself with that frame. You are an observer that needs to be fixing that frame, and you don't move from there. And then we said the reference frames do not really give us a way to measure anything. They define our point of view. But then at some point, we want to add, if you like, the sensing capability. They want to start measuring things. So that's what coordinate systems are. Well, what they do for us. And here as well, we need to be a little more accurate with the definition of coordinate systems. So coordinate systems let me first give a definition in English, if you like, are means to, it's becoming a little messy here. To measure, well, if you like, we can say are the means that we use to measure motion, to quantify things. Okay, so last time we've given this example here. Pick 3 points, as long as their distances don't change, 1, 2, and 3. You can create your coordinate system by picking, for example, E1 along this line, some intermediate vector E2 prime here. You do the cross product, normalize that, you get the E3 vector, and then E2 is the cross product between E3 and E1. And we said that we want to define basis that way. We were missing the first piece of information when we define a reference frame. I'm sorry, a coordinate system. What is that? Before the basis, what do I need to give you?
Choose the origin.
Right, choose an origin. So the procedure here is when you define a reference coordinate system, first thing you do is pick an origin. Call it O. What does that origin need to respect all the times?
Be on a point on the reference frame and not change.
Fixed in, let's call this reference frame A, right? The one that you woke up in the morning and you have chosen to use. Reference frame A, so it must be fixed in A. That's the point from which you're going to take measurements. You need to have some reference point. Without origin, there's no point in choosing the basis. Then you choose the basis. So define E1, E2, E3, and we decided that they're going to be, let's make it compact here in one definition, right-handed orthonormal. E1, 2, and 3 are at 90 degrees with respect to each other. They are of unit length, and we decided that we're going to stick with the right-hand rule, or the little diagram here that originates from my laziness in terms of remembering things, which I really like, and it's going to give me the sign of the cross products. That's a coordinate system. You have your frame, you have an origin, you can measure things from that origin, and you have directions to define vectors in that coordinate system. Okay. Everything clear at this point? That's exactly what we're going to do in every problem. You define reference frames. Well, we know we are in E3. You define reference frames. If you solve the problem without defining reference frame, you start drawing axes, we have a huge problem. You need to tell me what are the reference frames that you're going to use. We'll do that. Then you define the coordinate systems, then you use them. That is setting up the problem. You don't start drawing axes and writing formulas down before you do these steps. Now, kinematics is computing all those vectors that are rates of change of something else. So that means that at some point we need to start taking derivatives here. So what kind of mechanics are we dealing with in this class? I'm not going to do any Einstein relativistic mechanics, right? We need to know all the assumptions we are operating under. We assume that we are quite slow compared to the speed of light. So what happens in that case? Whatever Newton told us, right? Sir Isaac Newton, a long time ago, found out a few things that made our living much, much easier. What happens in Newtonian mechanics? Or I guess, what happens in relativistic mechanics that doesn't happen here? Time mass. So as far as we are concerned, in this class, we basically say that time is our independent variable. Time, t, does not change as a function of anything else. It is what it is. It keeps going. That's actually the only thing we can't control. We keep aging. There's nothing we can do about that. So in this world we're living in, much, much slower than speed of light, time is just going. And it doesn't change because of anything else. So if I pick a value of time and I freeze things around me, I'm going to see, for a particle, for example, a very specific position, velocity, and acceleration. And they all depend on time only. That is not true in relativistic mechanics. We have I think it's called the paradox of the twins. One travels away from the Earth almost at the speed of light. The other one stays here. Then at some point they meet again, and that's the paradox, because to meet again there may be some accelerations involved. So it's a long story, but the bottom line is that they actually age at different rates, because time is relative. It becomes relative. It's not relative here. It's just what it is. So we can start taking derivatives with respect to time without any issues here. But before we do that, let's formalize this fact in a simple expression. What that means is that it doesn't matter if I'm here or somewhere else and I'm attached to this table, to this board. It doesn't matter my reference frame. Time is going to be the same. And so t in reference frame A or t in reference frame B are going to be the same quantity, and I just can drop that notation and call it t. From now on, we'll do left superscript to indicating which reference frame I am measuring something. That's very useful. I can take derivatives with respect to time without caring about the variable t, at least. So let's start with something simple, like scalars. What could be a scalar quantity that I can measure? Mass, temperature, anything you like. So scalars have a beauty. They don't need us to talk about reference frames, right? And as a consequence, they don't need coordinate systems either. Remember, this comes first. If you have something that doesn't matter in which reference frame you are, coordinate systems are just a tool that you use in a reference frame to measure things. You can throw them away. And by the way, remember that a coordinate system must be fixed in only one reference frame. You can have infinite coordinate systems in a reference frame. But usually, you pick one, of course. You stick with that. So if that's true, and I say that I have some variable, let's call it y of time, which is a scalar function of time, of time t, I can just take its rate of change with time without thinking about in which reference frame I am. Doesn't matter. What's the definition of this? I know we've given up on this definition from basically the second day after we've seen it, because you use it a few times to demonstrate a few of those known derivatives, and then you never use it again. But that's That would be the actual definition of derivative, right? Oops, this is y of t plus dt minus y of t over delta t. That's true for every scalar. So if I have to deal with scalars at some point, I can just take the derivative without thinking about it too much. Okay. Vectors are unfortunately much more complicated. If I'm looking at a vector from a different reference frame, I have different results. So I brought some very high-tech tools that I grabbed coming out of the office, just for fun. So what's this? It's a box. Atlantis. It was $13. I don't know what it was inside, but it's a box. Pretty rigid. That's my reference frame. This is a vector. I'm going to do a very high-tech experiment. Let's say that this is the direction of the vector. The point is the tip of the pencil, right? And the other high-tech tool that I have here is Scotch tape. And I'm going to eat Scotch tape and chalk at the same time. And attach the vector to the reference frame. I don't see the vector growing or shrinking. It's a constant magnitude vector, which is fixed to this reference frame. This is what we're doing here. We're dealing with real stuff. We imagine vectors, but we can represent things. So if I move this reference frame around, but I am an observer in this reference frame, I am here on this corner, and I'm looking at the vector. Do I see it changing? It doesn't change. OK. But you do, right? So what I can write for that vector there, which is my friend B, I can write that d dt of B, and I'm missing something here. This is reference frame A, for example. In A is 0. 0 vector. If you take the rate of change of a vector, you get a vector. One comment. Now, this is a special case. Fixed.
Say B in A, like the rate of change in A of B in A.
B is a vector. It's reference frame independent. It exists. This is the operation of taking its partial, which is dependent on the frame. B does not depend on the frame. The frame is what you construct because you decide to observe things from there, but I can redo that motion that I've done before, I don't know what it was, without the frame. B is still itself, and it's still doing this. I decided to be in a frame here that it's attached to B, and I'm lucky to be there, and I don't see it changing. But that's a special case, right? So remember, vectors are reference frame free, coordinate free. They don't care about your point of view. They are what they are. Now, this operation is the fact that you're taking the rate of change depends on the frame. But the result you get, in this case, is 0, but it's a 0 vector. In another case where the result that you get is not a 0 vector, you will get something which is a vector. The result is another vector. The result is also coordinate free and reference frame free. It's another vector. Is the operation that you've done to obtain it that depended on the frame. But once you get the result, it's another vector. So what was true for B, it's true for whatever it is that you get when you take the rate of change. It's a vector. It's a quantity with magnitude and direction in 3D Euclidean space. These are hard things to understand, to really understand. They're not easy. They are just conceptual statements that you need to digest, thinking about them several times, because they're not easy. They're easy when you write things down. They seem easy, but what is behind this is not that easy. This is a vector. This operation of taking its rate of change is done in a reference frame. If I do it with respect to you, and you are sitting in reference frame B, I get something else. I don't know, C, some other vector. So the process that goes behind this, which is something very similar to that, is a limit, except now you do it with vectors, is the operation that gives you a different result, but the result is another vector. That was a very good question, though. OK, so we agree that taking the rate of change of a vector does depend on the reference frame. Let's say that now in this reference frame, and I removed the vector from the reference frame, but let's imagine it's still there. Let's say that I have a coordinate system also defined at some point. That means that I have, again, E1, E2, E3, fixed in A. That's my box, right? And I'm lucky that I can express, in the sense that I can express B in this basis. B is B1 E1 plus B2 E2 plus B3 E3. I guess this goes back to the question we just had. This is a representation of B in a chosen coordinate system. This could also be equal to some other representation, B1 prime, E1 prime plus B2 prime, E2 prime plus B3 prime, E3 prime, where these prime unit vectors are just another basis or coordinate system, part of a coordinate system in the same reference frame, or even in another reference frame. So you can represent the vector in infinite ways. It doesn't change the vector. OK, so let's say that that's what we have. Now, what is true if about E1, 2, and 3 if they're fixed in A? This is A. This, forget about the fact that it was B before. Now this is E1. It's fixed in A. That's what we just wrote, right? It's fixed. So what is true here is that D EI with respect to T in A, 0. Very nice. Okay, so in that case, if I am an observer in A and I calculate the rate of change of B, how do I do that? Can someone get me started here? Chain rule? Yeah, product rule. So first term will be d b1 dt. What are b1, 2, and 3, by the way? The scalars, right? So let's say that they are functions of time, right? As we did before. They can change with time, right? The scalars. So db1 of t in dt doesn't really need the superscript here. Doesn't change with the reference frame. E1 plus db2 of t dt E2 plus db3 of t dt E3. And to be thorough here, I would have to do b1 of t de1 dt in A plus b2 of t d dt of b2 in A plus b3 of t d b3 dt in A. Missing something? E2 and E3. Oops. At some point I switch to B. Thank you. E2, E3. But I just said that the basis is fixed in A, so this is 0. This is 0. This is 0. The 0 vector. That's easy, right? We made a comment last time, that's usually not the case. We don't have B. We're not able to express B many times in a coordinate system which is fixed in a reference frame. Again, satellite going to another planet. I can see it from here. I can measure things from here, from this reference frame. I can't from the sun. But I would like to know what's going on with respect to a potential observer on the sun. So say that we are in this situation now. Let's change a few things here. I still want the rate of change of B in A, but now this is fixed in B. So I have two reference frames now. That's fixed in B. But I want the rate of change in A. There's two things you can do. So basically, this is still valid. But now E1, 2, and 3 are fixed in some reference frame B, where I'm stuck in. And so this is not true anymore. This is B. But I still want d dt of B in some other reference frame A.
And the vector is still fixed in the reference frame A when we are trying to calculate when U1, U2, 3 are fixed in B.
I'm sorry, could you repeat the question?
But the vector is still, we are assuming that it's fixed in.
No, the vector is not, the vector is changing. See, the scalar components are changing. So the vector is actually changing. What I'm stating here, I'm just changing the name of the frame. So instead of being A, now it's called B, just to be consistent with the book. So forget about what I told you before. This is now called just B. That's where I can write the vector like this. I'm able to do it. I know that this is true because this is a basis fixed in reference frame B. So the unit vectors of the basis don't change in B. But now I'm telling you that I don't care about computing d of B dt in B, where I can write the vector, where I can express the vector with a given basis. I want to compute the rate of change of the vector B in some other reference frame. So I could have left A there and say that I wanted to do it in B, but then it would conflict a little bit with the way we're going to do things next. So we say that B is where we are. A is where we would like to be, but we're not there. But I really want that dB in dt in A. There's two things you can do. Rewrite B in A. Take a spaceship, go to the sun, become the observer that sits in the sun, define your coordinate system in the reference frame A of the sun, rewrite that expression, where now you will have different unit vectors, call it L1, L2, or L3. Actually, S1, S2, S3, this would be Earth, that would be the sun. So you could do that. You go there, you define your coordinate system in the reference frame A of the sun, and then you will have some B1 of T prime S1 plus B2 prime of T S2 plus B3 prime of T S3, where we need to state these every time. S1, 2, and 3 don't mean anything unless I state what they are. S1, S2, S3 is fixed in B. Right? Oh, I'm sorry, in A. That's what I would like to be. That would be nice. It's basically 99.9% of the times it's impossible. Not only it's impossible, and this is what, as a student, I used to do. I would make my life a living hell trying to take the vector I had to define and try to express it in the final reference frame where I would then take all the partials. Because once you write it this way and the basis doesn't change in your reference frame of interest, then it's easy. You take the partials of the scalar parts. Well, it comes down, we'll see in exercises, that is not that easy. It may make your life very complicated in the sense of the calculations you have to go through. And you may, at the end, stare at expressions that are not only ugly in the sense of how many symbols are there, they may not give you any insight. It's always nice to have an expression for velocity where you can actually understand the terms you're looking at. Well, if you don't instead do what we're going to do, you may just stare at formulas that don't make any sense, that you can't really comment on. This is the final result I got. It's a bunch of derivatives that I don't really understand. I hope it works. While the formula you want to get as the final result is something where you can make comments on and say, well, this makes sense. We'll see it. We'll see there's some problems. So the other option is that you try to relate the two frames. That will be called the transport theorem that we're going to derive completely next time. So I'm going to rewrite an expression here. So relate the two frames will allow you to remain in B, look at the vector, and take its rate of change in your reference frame where you are. And if you know how A is moving with respect to reference frame A is moving with respect to reference frame B, you can tell me what dA in dt is. So this is my end goal, is computing d dt of B in A. And the basis is fixed in B. So I'm going to write it again, dB1 dt E1 plus, I know it sounds like a repetition, but I have to make some comments on this. E3 plus, now those terms don't go away. I have B1 d E1 dt in A plus B2 d E2 dt in A plus B3 dE3 dt in A. Now these don't go away because E1, again, it's not fixed in A, it's fixed in B. Again, when you get a formula, this class, something at the end of a calculation, even a single step like this, stop and think about it. Don't just move forward if you don't understand what you have in front of you. So what this is telling me is that I have two components here that I see. This one here. What do you think that is telling me? That's what I had before when the coordinate system was fixed in the reference frame where I was taking the rate of change.
This is the value which remains constant for every reference frame.
The value that is constant for every reference frame. This is, try again.
Why didn't we, sir, write the equation in the terms of B1 prime and S1 when S1, S2, S3 is fixed in A and we're trying to find it in A? And even you do E3 earthquakes in B.
Well, what I'm saying is that it would be nice to be able to do this. It's not always possible. If you can, you can. You do it. It may be advantageous to you, but in most cases, you can't. You can't even describe these things. You're not there. You don't have the luxury of being on that frame. Remember, an observer, you're the observer, you must be fixed with the reference frame. Then you can go and define your origin, your unit vectors, and start expressing things in that basis. But if you're not able to be fixed with the reference frame, forget about doing that. So in astrodynamics, that's pretty simple to understand. But in many of the problems that we'll see, will be also clear why, even if you can do this, it may be easier to actually just go with something else, which again is a transport theorem that I don't have time to define this time. But if you know how the two frames are moving with respect to each other, you may compute the rate of change of B in the reference frame where you're not, with something that starts from here. But my point that I wanted to make here is, think about this first piece here. This is what? This is D B in dt in B, isn't it? That's where I am. That's what I see. These are fixed with respect to the reference frame where I'm sitting. I'm fixed in reference frame B, and the unit axis, the unit vectors, the basis is not changing with respect to me, who I am, and I am an observer fixed in B. So that's dB in dt. So what this formula is really telling me, this expression is telling me, is that the difference between the rate of change of B as seen by an observer fixed in A and as seen by an observer fixed in B is all this other stuff here. This is the difference between what the two guys see, the two observers see. Who is right? Both. They're both right. They're just looking at things from a different point of view. Unless you're biased, they're both right. And so this is really the difference between the two. And there is a way to, much better way to express this expression, this formula here, that will show you how the frames are moving with respect to each other. You can start to see that these terms here are really telling you how reference frame B is moving with respect to A. You can start to have that intuition, because E1, E2, and E3 are a basis which is fixed in B. It's glued to B. So if those three unit vectors are moving, that means that the reference frame is moving. Again, once you define a coordinate system, it's fixed to the reference frame. How those three unit vectors are moving in space, are changing in space, it's telling you how the reference frame is changing in space. They move together. There's no allowed motion, relative motion, between the basis and the reference frame, which is attached to that, the opposite. The reference frame and the basis, which is attached to the reference frame. So I can start understanding that these partials here, these rates of change of unit vectors of the basis, have the information of how B moves with respect to A. And we'll formalize that expression in a much nicer way, which will come down to being the transport theorem, which we'll start using every single time, because it will allow you to measure things in your reference frame, compute the rate of change of whatever is the vector that you're looking at in your reference frame. Then if you know how another reference frame is moving with respect to you, you can tell what this guy is seeing in terms of rate of change. This is a very powerful tool. You don't need to be in the sun to be able to tell me what an observer on the sun would see in terms of the spacecraft flying by. If you can measure that velocity and acceleration from here. Okay, we'll see you next time. Thank you.